Hello everyone. So in the last lecture, so we have discussed about the Taylor's experiment, that is impact of a bar of finite length. So we will continue this discussion. So what we discussed in the last class is the particle velocity of that impacted bar at different point of time. So we will again go through that discussion a little bit again. So basically what we have here is there are different steps of the sequence. So number 1, number 2, number 3, 4, 5 and 6. So we remember that this is C is the elastic wave velocity, and the plastically deformed part in sequence step number 2, that plastically deformed part will move at a velocity v, which is the plastic wave velocity. And so what we did in the last class, so we found out that for the region 1, here I wrote the region 1, or actually, or we can write it at R1. So I think in the last class we had this was written as R1, this region 1, and then R2 in this case, and then R3. So we will write R1, R2, R3. So the particle velocity for R1 case is just u, which is u is your impact velocity, and that is the velocity of the back portion of the projectile, or that impact bar. So this is actually, you can see that velocity of the back portion of the bar. So that is the impact velocity. So for region R1, it is u, the particle velocity is u, or we can write up equal to u. That means up is the particle velocity, general symbol for the particle velocity. For region 2, for R2, we can see that the region is behind the elastic wave front, which is elastic wave front is this one, and this is plastic wave front. So this in between the elastic and the plastic wave front. So now for particle velocity, up here will be u minus, so the particle velocity from the elastic wave that we calculated as sigma c rho naught. So sigma is nothing but the dynamic yield strength here. So so this one, and then if we talk about region R3, so then what is happening here is, so we have particle velocity will be that we talk that u minus twice sigma yd rho naught c multiply rho naught. Why it is twice sigma yd, we didn't discuss much about this. So what happens when the wave travels, if you can see from sequence 3 to sequence 4, what happens, the wave travels and then come back from the free surface. So what happens if we draw it here, this thing in a bigger way. So what happens is, this is the wave which is compressive. I will write C, I will write compressive wave, and this is the free surface, this is free surface. So this free surface will reflect the wave back, and that will be a tensile wave. So this will be a tensile wave, this is tensile elastic wave. So in the earlier discussion, in an earlier lecture, we we show that this reflected wave divided by this incident wave, that the stress is -1. That means for free surface a compressive wave will reflect back as a tensile wave. However, we also discussed that the particle velocity of the reflected wave, that is relation with the particle velocity of the incident wave, is +1. So that means whatever particle velocity here, that is UPI, and then UPR, the reflected wave. So this is the incident wave and this one is the reflected wave. So here also the particle velocity will be in this direction, sorry, PR, and this will be UPR. So we can see that both the sense of the reflected and the incident particle velocity is the same, or otherwise what we can also what we also discussed that for compressive wave. So we discussed that for compressive wave, UP and wave velocity, let us say we write as wave velocity as capital V, they have same sense, and for tensile wave UP and V has opposite sense, that we discussed earlier. So here you can see that for the compressive wave that particle velocity and the compressive wave velocity, but this is the wave direction, propagation of wave direction for compressive wave. So that UPI and this incident wave is in the same direction. Similarly, for the reflected wave, the tensile wave propagation direction is opposite to the UPR direction. So that is what in the that above statement says, that for tensile wave the UP and V are opposite sense. So it is because both UPI and UP are in the same direction. So we need to subtract that from the U, which is the impact velocity, or as we discussed that this is the velocity of the back portion of the bar. So ultimately, if we want to know the particle velocity inside the region 3 R3, which is actually left of that reflected or release wave front, this is the reflected wave front is so called release wave, then it will be U minus twice of that term sigma YD C by rho naught. So now we will discuss, we'll go ahead and we'll discuss that something else. I mean, we are continuing it. So so we want to see how much time it takes for this elastic wave to elastic wave, this is the elastic wave front, how much time it takes from this plastic boundary, that is that plastic boundary means we can call elastoplastic interface, or we can simply call plastic boundary interface or boundary. So because this side is plastic and this side is elastic. So so how much time it takes for the elastic wave front to go forward and reflect back at the free surface, reflect back and to reach again in the plastic boundary, elastoplastic boundary, and that is we can call the time taken is dt twice x by c. So this is x, so that is time taken to by the elastic wave front to travel from elastoplastic interface to the free surface and reflect back again to the plastic plastic boundary or elastoplastic interface. So this is twice x by c, and also for velocity of plastic wave propagation, that is v, we know that that can be written as dh by dt, because h is that thickness of the plastic zone. So, so we are talking of the same time interval dt. So suppose we have dh equal to v dt at the same time interval. So we will see that dh is the plastically deformed region thickness at time dt. So which we can write is from the above relation, we can write it as v twice x divided by c. So and also if you want to know the du, that is the change in impact velocity or change in the velocity of the back portion of the this back portion of the impacted bar, the bar. So that will be equal to something like u minus sigma y d c rho naught minus, which is before this before reflection, and then this will be equal to sigma y d c rho naught, so which is after reflection. So this will give us as du equal to capital U is equal to twice sigma y d c rho naught. So this is one relation, and then the plastic region advances a distance dx during time dt, that is, let us say twice x by c here from the above, twice x by c. So that we can write as dx minus u plus v multiplied by the time. How we got this? That is actually we earlier discussed that mass going into from the left side of the boundary to the right side, that is the virgin material goes inside the plastically deformed part, that is from the mass conservation of mass, we showed that the mass in is u plus v, which is because the back surface is going at a velocity u, capital U, and that plastic this interface is coming at a velocity small v. So if you want to know that mass going inside the this plastic region is actually the u plus v, because the plastic interface, elastoplastic interface, is going towards left, and then this back portion of this bar is going towards right at a velocity u. So this will be u plus v. We are writing minus because we are writing the plastic region advances, that is right to left. So it is minus u plus v, which is opposite to the impact velocity, so multiplied by the time twice x by c. So now from these discussions, what we can know is dh by dt. So dh by dt equal to v, which is plastic wave propagation velocity, the definition, and then dx by dt, which we just found out, u plus v. This is from nothing but this relation. So and then we have du dt, which will be equal to sigma y d rho naught x. How we got this relations? Is actually we have du equal to twice sigma yd divided by rho naught c, and if we replace this c, because c is nothing but we got that dt equal to twice by c, or we can write that c equal to twice x by dt. So if we replace this, let us say c minus twice sigma yd divided by rho naught twice x dt, and what we will get is here from we can cancel out the 2, and then finally we can end up with this relation. So from these two relations, what we can get is dx d capital U is equal to u plus small v rho naught x divided by sigma yd. So but from the conservation of mass we from conservation of mass we know that what we discussed in the earlier classes, plus a naught small v av. So that why the area is different, because the plastically deformed part and the other part has a different area. So this can be we can found out that small v is equal to a naught u divided by a minus a naught, and in terms of strain, so what we can do is a naught by a 1 minus a naught a multiplied by u, and this will give you 1 minus epsilon into u v. So what we got is plastic wave propagation velocity small v in terms of strain and the impact velocity capital U. So what we will do is we will substitute this v in this equation, above equation. So that will give us dx, that will give us dx d capital U will be equal to capital U plus u 1 minus epsilon divided by epsilon this rho naught x divided by sigma yd. So this part u plus u 1 minus epsilon divided by epsilon will give us u by epsilon, and then finally the expression will be sigma yd epsilon rho naught x. So we can write as dx by x rho naught sigma yd epsilon u du. So this expression, if we can use one earlier expression which is rho u square sigma yd is equal to epsilon square 1 minus epsilon, and if we can replace u from this relation to the other relation, and then if we integrate, what we can do is using this relation in the earlier relation what we got in the earlier slide, and then if we integrate it. So I am writing the final expression. I am not going into the detailed derivation of this, just left few steps, and then finally what we can get is ln of x square integration 1 by epsilon d epsilon square 1 minus epsilon, which will give us integration by parts, and that will give us as which is just integration actually u dv, let us say u dv is equal to uv minus v du. So, applying that, what we will get is epsilon square epsilon into 1 minus epsilon minus epsilon square minus 1 minus epsilon and d 1 by epsilon. So, and d 1 by epsilon actually d epsilon will be minus 1 by epsilon square. That means what we can get is epsilon square d 1 by epsilon differential of this and is equal to minus differential of epsilon. So, that way we can write it as 1 minus epsilon plus 1 minus epsilon d epsilon, and that can be written as again epsilon when we do the integration with a constant of integration k, and we will use some boundary conditions here, like at x equal to L, L means first the initial length of the bar when impacting the rigid wall. So, this length is L. So, when it impacts the rigid wall, so let us say the strain is epsilon equal to epsilon 1, let us assume that epsilon is equal to epsilon 1, and then if we use that relation, so which will give us as the constant of integration k, which will be equal to ln capital L square minus 1 by epsilon 1 plus ln 1 minus epsilon 1, and that will give us if we replace that in the earlier expression. So, we will end up with ln small x capital L whole thing to the square 1 minus epsilon minus ln 1 minus epsilon minus 1 minus epsilon 1, there is the constant of integration. So, 1 minus epsilon 1. So, again at x equal to capital X, so epsilon equal to 0 when this actually the end of the deformation, when the elastic wave that is released from the free surface, that is back surface of the impacted projectile and that bar. So, that okay, I will draw it here. Suppose when this is the rigid wall. So, the final shape of the projectile will be like this. So, what happens when the release wave goes back from the free surface, this is release wave, and then meet the plastic wave here, plastic wave. So, then it will, the deformation will end and the strain will be 0 at that point. So, this distance we can call it as x, and then total distance is L1, the final, this is the initial configuration and this is the final configuration. So, now if at small x equal to capital X and epsilon equal to 0, so then what we can get, this relation can be written like 1 minus, because epsilon equal to 0 in the above expression, 1 minus 1 divided by the 1 minus epsilon 1 plus ln of 1 minus epsilon 1. From an earlier expression, what we know is rho capital U square sigma yd, which is dynamic yield strength, is equal to sigma 1 square divided by 1 minus sigma, sorry, not sigma, epsilon 1. So now what we can do is, if we eliminate epsilon 1 from these relations, this a and b, if we try to eliminate epsilon 1 from a and b, so we will end up with a expression of L1 L2. We can find out L1 is that final length, and divided by L is a function of rho capital U square sigma y d. So, is a function of this. So, we can Taylor actually plotted this and proved this model with experiment. So, we can get both L1 by L and L1 minus x divided by L. So, these can be obtained if x by L, if so we can get these if x by L and epsilon 1 known. So, what we know from the Taylor's plot is rho capital U square sigma y d, which is 1, 2, 3, 4, 5, and in this direction L1 L, or maybe we can plot even L1 minus x by L, both we can plot in the y direction. So, for L1 L plot, this looks something like this. So, this is L1 by L and this is 1, let us say 0.8, 0.6, 0.4, sorry, 0.2, 0.2, 0.4, 0.6, 0.8. So, and also for L1 minus x2, this will look like something like this. So, this is L1 minus x by L. So, basically so whatever the model, the theory Taylor proposed is and then experiments, observed results show very very close to this. So, prediction is very good when this value is rho u square by sigma y d is around 0.5, but if you go away, so this will show some deviation. So, the prediction is not so good. It is something like this. These are all from the Taylor's original experiments and then theoretical predictions. So, basically so if it is rho equal to if it is not rho, sorry, rho u square divided by sigma y d is equal to 0.5 0.5, the shape will look like this, and the prediction is good. But then when it has higher value, so rho u square sigma yd is equal to let us say this is the wall, let us say. So, this if it is equal to 1.63, so it will be look like this, and if it is even higher value, so it will take a maybe this kind of convex shape, and this is rho u square sigma yd is 3.2. So, now this way we call this as mushrooming effect. The shape of the bar will look like this, and although it is little not exactly correct, so it may be the first one we can draw little longer. So, if we go this way, and if it is the impact velocity is very high, so this is increasing impact velocity. If it is very high impact velocity, very high impact velocity, the shape of the deformed projectile or bar can be very different, and it can even take a concave shape. So, for this Taylor's experiment is for steel projectile or steel bar, and for steel bar this value 0.5 is can be the impact velocity is like 250 meter per second. So, you can imagine the how fast it will be for the other cases. One important result of the Taylor this analysis or the Taylor's experiment is the velocity of plastic wave propagation. So, velocity of plastic wave propagation we wrote it as dh by dt. So, that is nothing but the change in the total distance of the elastoplastic interface from the impact plane. That means whenever you have some deformation like this, so this elastoplastic interface, so distance here is h. So, this distance how fast it is moving away from the impact plane, and it will give us the plastic wave velocity. So, now the total time from our the initial length L to final length L1. So, the total time is like what we can find out from this is rho x sigma y d du. So, how you got is earlier one expression we know that du by dt is like sigma y d rho naught x. So, we are assuming rho here, not rho naught, let us say. So, that is the expression we got. So, this is the total time, and from another equations we have the u in terms of strain. What we found is sigma y d by rho and epsilon square 1 minus epsilon entire thing square root. So, what we can find is if you replace this one u in this du, so what will happen is d epsilon 1 minus epsilon. So, this will take a shape like it's like d u v dx, which will be like v square v du dx minus u dv dx. So, that way this expression will be like 1 minus epsilon into 1 plus 1 minus epsilon, which is square of the square root, and then e 1 by twice 1 minus epsilon. So this will give us something like 1 minus 0.5 epsilon divided by 1 minus epsilon to the power 3 by 2, and so basically d e 1 minus epsilon square root will be equal to 1 minus 0.5 epsilon divided by 1 epsilon to the power 3 by 2 d epsilon. So finally, if we want to get an expression of the t, which will look like rho by sigma yd, square root of the whole thing into multiplied by the integration of x will be here, and 1 minus 0.5 epsilon 1 minus epsilon 3 by 2 d epsilon, and the entire thing we will take a limit from 0 to epsilon 1, because at the x equal to L, the strain is epsilon, and then x equal to L, and at the final the strain will be equal to 0. This will be 0, and we have a minus sign here, so this will be, now we can take from 0 to epsilon 1, we reversed it with the minus sign. So this is the total time, and we have a relationship with rho sigma yd. We have a relation like this, and then what we can have from these two, u t l epsilon 1 1 minus epsilon 1 square root 0 to epsilon 1 x, L is coming for this L on the left hand side, and then u, also the u, the u is nothing but also on the top. So okay, we already have that, sorry, so we don't need to write this u here. So this u will be coming that way, and this L is from here. So 1 minus 0.5 epsilon divided by 1 minus epsilon 3 by 2 d epsilon. So if this relation, if we want to do numerical integration, so if we want to do numerical integration, so numerical integration of the earlier expression will give me some curve, so that will be that can be in terms of ut by L, and this way you can have HL. H is the thickness of the plastically deformed region. So so that is like if you have this as 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 and 0.7. So here 1, 2, 3, 4, 5, 0.1, 0.2, 0.3, 4, 5. So what will happen is this will look something like this. It's kind of a straight line, close to a straight line. So this will be for this one is for epsilon 1 equal to 0.5, and this one is equal to epsilon 1 equal to 0.7. So the value rho u square sigma yd is 0.5 as we discussed, and this is the actually end state here. So it will end here. So rho u square sigma yd, it is 1.63 that we have earlier even shown that one of our this 1.63, the same ratio here we are taking. So now actually we can write as this h by l, ut by l is nothing but that 1 by u h by t is equal to 1. This will be equal to close to 1 if strain is or you can write strain epsilon 1 is equal to 0.5, and then and if it is if will equal to 0.5, if 0.5 epsilon 1 equal to 0.7. So here we can see these two plots, say with the same plot in the curve. So the basically this h by t is nothing but the plastic wave propagation velocity. So that means your v by u is equal to 1, so which is the impact velocity, u, and this is plastic wave propagation velocity, they are equal for our strain that is equal to epsilon 1 is equal to 0.5, the maximum strain, or if it can be equal to this is small v actually, small v, and capital U is equal to 0.5 for epsilon 1 equal to 0.7. So yeah, this is mostly it's almost proportional. So what we got here is HL by L nearly proportional to UT by L. So this is what from the Taylor's experiment. So we will continue this discussion. We have some more discussions on it for Taylor experiment, and then we will start another chapter of shock wave. So before going to shock wave, we will have a little discussion about this Taylor's experiment. So we will try to have some try to solve some numerical problems. Thank you.